The next topic in regularization is the cost function, and I'm going to show you how it changes and why. For example, if we have data with the price of a house based on the size of the house, we might think on a quadratic function like this to predict the prices. And we end up with a curve like this. This curve gives us a pretty good fit, but if we want to take an overly higher order degree polynomial, we end up with a curve that might look like something like this. This curve fits the training set really well, but it overfits the data and can't generalize well. Consider the following. Suppose we are to penalize and make the parameters theta3 and theta4 really small. Here is our optimization function, and we need to minimize it using the square error function. So if we make theta3 and theta4 1,000 times bigger, and we minimize the function, we are gonna end up with these values of theta3 and theta4 really close to 0. And we might end up with something that looks like a quadratic function, but it has some small contributions from theta3 and theta4. More generally, here is the idea behind regularization. The idea is that we have small values for the parameters. We end up with a simpler hypothesis, and we end up with smoother functions, as well as we end up with a hypothesis less prone to overfitting. For example, if we are trying to predict the house prices, we might end up with 100 features like size, where it is, how old is the construction, etc. And we might end up with 100 parameters or even more. If we have something like this, it's really hard to know which ones to pick to minimize them, because there are too many. So in regularization, we are going to modify the cost function and add this term to our minimization problem. To shrink all the parameters from theta1 to theta100. And we start in 1 because we don't want to minimize theta0 by convention, but it makes little difference, just by convention. This is our cost function, and this is our regularization parameter. And what lambda does is control the trade-off between fitting the training data really well and keeping the parameters small in order to keeping the hypothesis simple and avoiding overfitting. By doing this, we pass from a curve like this to something like this, which isn't quite a quadratic function, but it's much smoother and much simpler. That gives us a much better hypothesis. What happens if we set lambda to a large number, something like this? Well, if we set lambda to a large value, we might end up with penalizing the parameters theta1, theta2, theta3, theta4, etc. very highly. And if we do this, all these parameters will be close to 0. And if we do this, we end up with a straight line, something like this, because theta0 is 1. We end up with a straight line, and this is an example of underfitting. and the result is an hypothesis with high bias. In order for regularization to work, we need to choose a good value for a lambda parameter, not too big and not too small. So, what happens if we set lambda to a large number? Well, we might end up with 4 cases. The first is the algorithm works pretty fine. The second is the algorithm fails to eliminate overfitting. The algorithm results in underfitting, fails to fit even the training data, and the gradient descent will fail to converge. And that's it.